Assalamualaikum warahmatullahi wabarakatuh. Good morning, students and maybe also teachers. We will move forward to study more deeper the topics in statistical mechanics. We have already discussed in detail how to calculate the partition function of assembly by first determining the particle energy and then develop calculate the partition function of particles and then derive the partition function of assembly, and then from that partition function we derive many thermodynamics or macroscopic properties of the assembly. Until the last discussion, we focus on assembly containing particles with discrete states. The particles have only energy in a certain level. The particle cannot have any energy, cannot have arbitrary energy, but the energy is determined by the quantum number that changes according to the integer difference. But in many cases, we will meet the assembly containing particles with energy continuums. So in that case, we must calculate the partition function in a different method. In case of assembly containing particle with discrete energy, we calculate the partition function using the summation. As we have discussed earlier, that for assembly containing particles with discrete energy, the partition function is calculated according to the summation of this term. ds is the generation, and then this is exponent s over kt. This is the number of arrangement of one particle. This is the particle energy, and this energy is discrete. 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 For example, for atom vibrating in crystal, we have discussed that atom in crystals, we have the energy equation is given by nx plus ny plus nz plus 3 over 2 s omega 0. Here this integer, this is 3 n are integers. So for the case of energy that depend on the integers, we determine the partition function using this summation. But what happened when the particles inside the assembly, this is assembly, our assembly, this is particles. The particles does not have a discrete energy, but the energy is continuum. The most common example of such assembly is assembly of gas. Assembly of gas containing particle moving in three-dimensional, in the case of three-dimensional, with the kinetic energy can have any value from 0 to infinity. So the kinetic energy of particle in gas is not depend on the quantum number, on the discrete quantum number, but can have any arbitrary value from 0 to infinity. Because the energy, the kinetic energy are continuum, kinetic energy continuum, can have any value from 0 to infinity, we cannot calculate the partition function using these summation symbols. because we don't have a symbol like S in this case of in the case of kinetic energy, because the kinetic energy is the continuum quantity. So, for the case of assembly containing particle having continuum energy, we can transform this summation into the well-known integral. So, in case of assembly containing particle with continuum energy, the summation for the case of discrete assembly is transformed into the integral form. So, in case of this is for discrete, discrete. This is for continuum energy or state. In this case, we have the expression for the partition function of particle is the summation of this one. E epsilon s is the energy of a particle. This is a discrete energy depends on the quantum number like n. And in this case, we have to transform the integral symbol in the summation symbol into the integral symbol. And this is the energy of particle in continuum expression. So, and now, if we have an integral, we must have the symbol like D. D, and to transform this one, this is the number of arrangement, the number of states in discrete state. In this discrete situation, we must transform into some similar expression in the continuum energy assembly having continuum energy. So, in case of an assembly having continuum energy, we have transformed from this summation into this integral. Now the problem is how to calculate this one. What is this one? When we discuss the assembly containing particle, if we transform from the summation into the integral, we have it means that we transform from the summation into the phase space. This integral must be calculated in phase space. Phase space is governed by the spatial coordinates and momentum coordinates. If particle have a spatial position x, y, z, and the particle have also three momentum px, py, pz, and x, y, z, px, py, pz govern the space named phase space. So the phase space for one particle, the phase space of one particle contains 6 coordinates: x, y, z, px, py, pz. So for particle in three-dimensional space x, y, z, the particle has 6 coordinates in phase space: x, y, z, px, py, pz. If the particle is in a one-dimensional space, only x, the particle has 2 coordinates in phase space, x and px. Particle in a two-dimensional space, the particle has 2 coordinates in phase, x and y, but in phase space, the particle has 4 coordinates, x, y, px, and py. So in case of one particle, we have 6 coordinates in phase space. So the element, the volume element in phase space belongs to one particle is d gamma, equals to dx dy dz dpx dpy dpz. This is the volume element in phase space. It contains the volume element in space and volume element in momentum space. This is only space. This is momentum. Momentum and space, they govern the phase space. So we have 6D in this phase space only for one particle. But if we have two particles, each will contribute 6 elements. So for two particles, we have 12 elements of phase space, the 12 coordinates of phase space. Now we focus only one particle. So in our integral, the transformation becomes, this is we will determine later, an exponent minus epsilon of a kt dx dy dz dpx dpy dpz. This is the element, volume element in phase space belong to one particle only. So the next one is, what is this parameter? What is this inside? So in case of one particle only, this is the density of states in phase space belong to one particle. You see the density of states in phase space of one particle only. Now we consider only one particle, and this one is the density of space, density of states in phase space belong to one particle. Now this has been calculated in a lecture of statistical physics. This, for one particle, the density of states in phase space is 1 over h power 3. This is the Planck constant. So the transformation from the summation into integral for the case of one particle, for one particle partition functions, becomes this one. The complete expression for the integral becomes 1 over h power 3 exponent minus a particle energy of kt dx dy dz dpx dpy dpz. And because we have 6 elements or d, then the integral becomes 6-fold. 1, 2, 3, 4, 5, 6. This is the z partition function of one particle with continuum energy. We have to solve this integral, 6-fold integral. This is the particle energy in continuum expression. It is the same. We have changed from the summation into integral in 6-fold integral against dx, dy, dz, dpx, dpy, and dpz. This is only for one particle. We will solve this expression. For simplicity, we can write this one as, because this is constant, we can move outside the integral, exponent minus epsilon of a kt dx dy dz dpx dpy dpz. To simplify the expression, even we have a 6-fold integral, we sometimes write only one integral symbol. But although we use a one integral symbol, the meaning is 6-fold, because we have 6d here. we have to integrate over dx, dy, dj, px, py, and pz. So even we write only one symbol, but the meaning is six-fold integral. Integral over six coordinates in space and in momentum coordinate. So sometimes if we look at only one symbol, but this has 6D, the meaning of this one integral symbol is this one, six-fold integral symbol. We will solve this for the case of an ideal gas and will determine the result, the partition function of one particle inside the gas. And then from the partition function of one particle, we will calculate the partition function of an assembly, the assembly of the gas, the assembly. And then from that partition function, we finally derive the equation for gas. We know that for ideal gas, we have the most well-known equation, PV equals to NKT. And we will solve later then. Using this approach, we will also obtain that equation for gas. For ideal gas, we will obtain the same equation as we have already learned in the thermodynamics or in the statistical physics lecture. We will discuss in later.